So what we're going to be talking about today are some basics of what is a map and the measurements that go into that map, ways in which to verify that a map is appropriate, and also some basic troubleshooting that can be done off-site, as well as what types of things will be done when and if a child is referred back to their programming center for investigation to see if changes to that map are necessary. So the first topic of what is a map. The map is that individualized listening program that's stored in the memory of the processor. It is based upon that individual's responses to differences in loudness and pitch, and although it is usually written in all capital letters, it is not an acronym and it stands for nothing. So it really was meant by the early developers of the technology that to be an expression sort of like how one would use a roadmap to get from one location to another. The sound processor map is how the stimulation and the sound gets from the external environment to the internal device. So just a little trivia for you there. One thing to remember when we're talking about the map for a cochlear implant is that we are utilizing some physical limitations that are existing in the environment that we're working within. Because what we're doing is we're taking the 120 decibels of a acoustic hearing dynamic range that exists for anyone with normal hearing, and really trying to focus on the 40 dB or so of speech that is the most important aspect of that information. And that varies whether that is loud speech or someone shouting or more conversational speech, as well as soft speech. And what we're doing with that 40 dB of information that's coming in through the system is then trying to compress that into a range of 2 to 20 dB of electrical hearing that any one individual may have. And that 2 to 20 dB of electrical hearing clinical dynamic range that's available is a physiological restriction of the auditory system. So it is a universal. It doesn't matter which sound processor someone's using or what the levels of their map are set at. We're still having to take that 40 dB of acoustical information and present it in this 22 to 20 dB range of electrical hearing. And there are a number of systems that are built in to the sound processing algorithms that enable us to do that. Some of those are included in the items that we're going to talk about in terms of the basic parameters of the map. And we're going to talk about these in order of how they tend to occur in a programming session. So if any of you have done programming of cochlear implants or observed a programming session, the first step is always doing an impedance measurement where we're looking at the telemetry system of the device. And telemetry is a fairly generic word that's used quite a bit in various areas of general medicine. It is strictly translated as a remote measurement system, and where most people are aware of telemetry is in cardiac cases where there are a number of patients in a cardiac ICU who are all on monitors, and at the nursing station there is almost like a command central where they're able to look at all of those monitors and track how each person is doing remotely, based on the measurements that are being taken from those cardiac monitors. And so this information is very beneficial in monitoring the system, as well as providing additional information and additional data to help us with optimizing the programs that are being used with their cochlear implant. When we talk about telemetry, there are a number of different measurements that are actually taking place. Telemetry is sort of the umbrella term. And one of the measurements that we're doing is impedance telemetry. And that is looking at the opposition to electrical current flow. So the impedance test will identify if there are any short or open circuit electrodes on the device. And once those electrodes are identified, they are eliminated from use in the map. We're also able to look at some additional telemetric measures, which are the voltage compliance and the NRT, or neural response telemetry. And we're going to talk in quite a bit of detail about both of those as well. And when we use all of these measurements together, that's actually providing us with the information that's necessary to determine what the power level is that is required to send the signal across the skin to maintain a consistent communication between the external transmitter coil and the internal device, what the battery suitability is for that individual map and processor. So are they able to use the smaller rechargeable batteries versus the larger rechargeable batteries, or using alkaline batteries versus rechargeables, as well as calculating those battery life estimates that also are present in the software and the map reports to let you know what the estimates are of minimum battery life for each of the maps. The RF link, or the radio frequency link, that exists between the transmitter coil and the internal component of the cochlear implant system can range from a very robust and strong link to a weak or intermittent link. And that communication can be influenced by a number of factors. Some of them we have control over in the map, and some of them we don't. So the first one listed in this list is an issue that is unfortunately completely out of our control, and that is the thick or thinness of the skin flap that's in place, as well as the hair that an individual has. And so if someone has very thick skin with very thick hair, that's going to increase the distance between the transmitter coil and the internal component of the device, which is going to make that communication a little bit more difficult because of the distance that the signal is having to travel. But the power level that's set in the software, the battery options that are being used, the levels that are set within the software are all aspects that we have control over, and are components that we can change so that we can try and maximize that link and maintain as robust a link as is possible at all times. If one of these settings is out of the appropriate range, then you can have some symptoms such as intermittency, decreased battery life, that are related to those settings and not necessarily to the actual link between the two components. When we do the telemetry testing, and if any of you have seen the reports that come from the custom sound software, you can see that the telemetry testing is done in 4 different modes. And we have a schematic of the electrode on this slide where these are the intracochlear electrodes, the 22 electrodes that are in the cochlea. And then we have the 2 ground electrodes, one that's on an additional lead that comes off the electronics of the device and is placed under some muscle tissue, and the other that's on the body of the implant itself. And so when we test the impedance telemetry, we're testing in the common ground mode, where we're testing each individual electrode within the cochlea as it is grounded to all of the other electrodes that are part of that array. And so we have to remember when we're dealing with cochlear implants, we are talking about an electrical current. And just like when you are jumping the battery of your car, you always have to ground that black clip to something outside of where the battery is, so that as you're sending the current, you're not overproducing the electricity that's going into the battery and blowing up the battery. So to have a complete circuit, we have an active electrode and a ground electrode. And so we have that common ground mode where we're testing each of those electrodes within the cochlea, and then we test each of those grounded to the MP1 electrode. We then test each of the intracochlear electrodes grounded to the MP2 electrode, and finally we test each of the intracochlear electrodes to the MP1 plus 2, where we're tying both of these ground electrodes together, and that is the mode in which the devices are programmed. And so when you get the telemetry, the impedance telemetry report, you'll see 4 different values for each electrode for each of the different modes in which the impedance has been tested. As I mentioned before, that we're looking for either open circuit or short circuit electrodes. An open circuit electrode is a very high impedance where there is no resistance to that current that's being delivered, and a short circuit is a very low impedance. And so the values for those cutoffs are listed here, and anything in between that is within the acceptable range. And when we run impedance through the software, it's very obvious if there is an open or a short circuit. The indicator for that electrode will change from green to red, and once it has been identified as a problem electrode, it is removed from the map and will not be included in future tests unless the audiologist purposely goes in and flags the electrode as a problem to remeasure that. The values are important because we want to make sure that they're within that acceptable operating range, and the pattern of the impedances is important. We tend to see a fairly smooth pattern to the graph of where those impedances occur, and it's unusual to see a spike of one electrode that is very different from the electrodes on either side of it. You can only measure telemetry if the coil is over the implant. So it is important that the processor and the transmitter coil be in place in order to do this measurement. If an implant is non-functional, then we are unable oftentimes to measure telemetry, and that's often one of the first signs that there's a problem with a device. So, in addition to the impedance information to know whether the device is operating within that typical range, we also use the impedance values to determine how much voltage is available. And so what we're looking at in the compliance telemetry is there enough power available for that electrode to provide the amount of um, intensity of the signal that is needed for this individual. And so if we look at this graph, what it is showing you is it's a pulse that is occurring, and the first line is the base level of presentation of the signal, and then it's being increased by a certain amount. So this is theoretically a 10 unit increase in output. So you're asking the device, instead of presenting at 120 current level, let's present at 130 current level. And because you can see that there's a nice equal increase in output of that pulse in both the negative and the positive side, there is enough voltage available to support that requested increase in power. On the right side of the screen, you're not seeing that nice equal increase in output. There's some distortion that's occurring when that increase in current is made between those two levels. And there is also limits that are being placed on the increase on the bottom graph. And the best way to think about this, when I first started having to talk about it and explain it, and really the best way that I understood it at first, was taking it out of the realm of cochlear implants and electricity and thinking about it in something that's much more real to probably every single one of us, and that is our bank account. And so your voltage compliance is your bank balance. And is there enough money in that account to cover the next check that you're going to write? And if you start to get near the end of the 2 weeks before your next paycheck, you have to pay close attention to how big of a check you're writing to make sure that there's enough money in the account to cover that next layout of funds. And so this is making sure that there's enough power in the bank to cover every time there's a requested increase in the amount of current that's being delivered to that device. And so sometimes you may hear an audiologist talk about needing to make changes to the map because an electrode was out of compliance. And what that really means is that we're unable to provide enough power to present at the level that that individual may need for that electrode. And the way that that looks in the software is that the channel bar within the software turns red. So just to give you a quick overview for, again, those of you who have not been able to see a programming appointment, what this screen is showing you, you've got your electrode numbers along the top from 1 to 22, with 1 being your most high frequency and 22 being your most low frequency. The green indicators are your threshold levels, and the red indicators are your comfort levels. There are a number of details about the map that are shown on the far left side of the screen, and then all of the controls in terms of presenting information, presenting the tones and manipulating the levels are here on the right side of the screen. And so when those channels turn red, that means that either the threshold or the comfort level required for that channel have surpassed these little red hash marks that you can see on these low frequency channels probably better. And so you have two different hash marks that are showing, because depending on the battery that an individual is using, there will be a different compliance limit in place. And typically, the rechargeable batteries will provide a higher compliance limit than the alkaline 675 batteries. The reason that this matters is really because if you are presenting on an electrode that is out of compliance, you're most likely not delivering the level that you think you are. And in some of our old systems that don't have telemetry available, that was very often the case, where we would be thinking that we're presenting at 175 units, but because that electrode was out of compliance, we're presenting something less than that, and it could be significantly less than that. Because the loudness isn't growing with that increase in current, it's providing a distorted sound to that implant recipient, and they're not hearing the appropriate changes in loudness because of operating in that out of compliance state. They may also experience poorer battery life because the system is trying so hard to keep up with those electrodes that are out of compliance. It's expending a lot more energy and utilizing much more of the battery, and therefore could cause some additional inconveniences and problems for that recipient as well. So what the audiologists who are programming have been instructed to do is that if there are channels out of compliance, the first thing that we try and do is just reduce that comfort level, or the C level, to bring them into compliance. And if it's just 1 or 2 units, for most individuals, that's not something that they will hear a difference. Whereas keeping that electrode out of compliance, they will definitely hear a difference for the negative. In some cases, we do have to make some additional changes, and those have to do with the stimulation rate and the pulse width that's being used when we're working with the device. And so if we look first at the pulse width, again, when we are presenting the signal to the device, we are presenting a biphasic tone, so a pulse. So it has 2 phases to it that are equal and in opposite directions. So you have the positive phase and then an equal negative phase. And when you go from this width of a pulse to this width of a pulse, what happens from a perceptual standpoint is it requires less current to result in the same perception of loudness. And if we look at the continual increase in that pulse width, what you'll see from the narrowest, which is where we would typically start, and perhaps someone is crossing that compliance limit and having an electrode that's out of compliance, you're then able to go to a wider pulse width, provide the same amount of loudness perception, but because it's being spread over a wider current, you're no longer coming up to the compliance limits. And so again, taking things out of the cochlear implant world, this would be analogous to having a 6-ounce cup full to the rim and trying to walk with it without spilling. you're going to continually um, spill some water and probably make quite a mess. If you were to take those same 6 ounces of liquid and put them into a 10-ounce container, all of the sudden you have some nice headroom to allow you to walk without spilling. And if you took it to a 20-ounce container, you'd have significantly more headroom that you would have available to you. All the time using that same amount of liquid that you needed to have a nice drink. So pulse width changes are available to you to improve that range of loudness primarily, and to give access to louder sounds without causing the electrodes to go out of compliance. The way that the compliance is measured, and I always have to laugh when I use this slide because it was a slide given to me by one of our engineers, and only an engineer would see a calculation that had 10 to the negative third power as a simplified calculation. But what this is just providing some examples of is showing why a given set of parameters may be appropriate for one individual's map and yet inappropriate for another's. So for this example, there are 10 volts that are available for this implant. And we want to stimulate at about 220 current units, which is 1 milliamp. And the impedance on this electrode is 8 kiloohms. And so what we're doing is we're doing the calculation of the impedance times the rate. And so we are taking that value that we want to stimulate at, that 1 milliamp times 10 to the negative third power, times our impedance times 10 cubed. And so this gives you 8 volts. And because you have 10 volts available on your implant, this is something that is accessible and can be, this level can be presented for this electrode. In our second example, everything is the same except the impedance on the electrode has gone from 8 kiloohms to 14 kiloohms. And so now what happens is we've got a requirement of 14 volts. And because we only have 10 available in the implant, we can no longer stimulate at this level or for this individual because we don't have the voltage supply available to present that 228 current units. And so this information, this level would be out of compliance for that individual. So you may sometimes look at a map or be in a situation where recipients seem to have very similar programs, and yet one is able to report different loudness or do differently with their device, and it has so much more to do with many more variables than what we're able to sometimes see on that piece of paper. If we look at the threshold and comfort levels, those are probably the aspects of programming that people talk about the most. The threshold is that lowest level of electrical stimulation that's required on each electrode. And accurately measured threshold levels allow the recipient to hear the softest sounds of speech and environmental sounds, incidental speech. We tend to focus a little bit on making sure that T levels are as accurate as possible, just to make sure that all of the important information that we want processed by the system is being received. At the opposite end of the spectrum are our C levels or our comfort levels, and that is the maximum level that a recipient can comfortably tolerate at any given time. So it's not the level at which, with white knuckles and teeth gritted, they say, oh yeah, that's okay, but a level that is truly comfortable. And what the C levels do is prevent any sound in the environment from becoming uncomfortably loud. All active electrodes in a map will have a T and a C level. Those levels, while they're individualized, do tend to be fairly similar with all of the current devices that are on the market. The range between the threshold and comfort level is described as the dynamic range of that channel. And those T and C levels will change over time, especially in the first 3 to 6 months after implantation. We always want to remind people that recipients should not and cannot trade processors. For most devices, the Implant ID feature will prevent this from happening, but we want to reduce the likelihood of individuals trying other people's processors on because they could be programmed dramatically different and could result in either no stimulation or painful stimulation for the person for whom that device was not programmed. If we look at a map printout, your threshold and comfort levels are listed on that map. So again, you've got your channels going from 22 to 1, and then your threshold value for each of those electrodes, your comfort level value for each of those electrodes, and the dynamic range for each of those electrodes. We measure those levels through behavioral measurement. It's the same condition response task that we use for sound field testing. Many pediatric cochlear implant centers are also equipped where they have their programming equipment in a room with a VRA setup so that they're able to use all of the same tasks that we use with traditional pediatric audiology for programming their cochlear implants. We do have additional tools available to us from an objective standpoint. Neural response telemetry, the use of electrically evoked stapedial reflexes, as well as an electrical auditory brainstem response. If any of those objective measures are used to assist in the setting of levels of the maps, those will also be listed in the map report where you have the objective levels column, objective measures column. A couple of things to remember about TNC levels is there's no target. We don't want everyone to have a threshold level of 140 units and a comfort level of 180 units. As I've been using the terminology in terms of the units in which TNC levels are measured, they are in current units and not in decibels. And there's no relationship between threshold and comfort levels with a cochlear implant and preoperative sound field thresholds or the amount of residual hearing an individual had prior to surgery. So there's no way to sort of predict what those levels are based on their audiogram going into the process. For any map that has all 22 active, we will have access to the full frequency range available for the device, which is from 188 Hertz to 7,938 Hertz. For the nucleus cochlear implants, we have 3 different sound coding strategies that are available. Most recipients use the strategy that's called ACE, which stands for Advanced Combination Encoder. And what that is, as its name suggests, it is a combination of the other two strategies that are listed below on the slide of speak and the CIS strategy. And it takes the best aspects of each of those other two strategies and combines them together. While, as I said, most recipients do use the ACE strategy, the other two are also available if there are certain situations where that may be necessary. The number of variables within each strategy numerous, and so the most important one probably to pay attention to is the rate. And so within the ACE strategy, you may see different rates in which the device is being stimulated. And if you look at the MAP summary report, you will be able to see what strategy is being used in each of the different program locations. On the sound processors, they also have a sensitivity control. And the sensitivity control determines what the softest level of sound is that will be picked up by the processor. The default is 12, and sometimes that level has been fixed or locked by the programming audiologist to prevent any unintended adjustment of that parameter. And if we look at the reason why the microphone sensitivity is set at 12, we'll use this graph. And when I'm looking at this graph, the line here in between the yellow and the green is your T level. And your the line between the green and the red is your C level. Anything that's occurring below your T level, you're not hearing, and anything that's occurring above your C level is operating within the AGC range, or the automatic gain control range of the processor, and therefore is being compressed so that it's not being stimulated above that C level. And so with a sensitivity of 12, what's happening is any sound in the environment that's happening around 25 dB SPL is what is being picked up by the microphone of the sound processor and presented at the threshold level. A sound that is at 65 dB SPL is being presented at C level. And so you have that range of stimulation that is occurring between your T and C level. If someone were to shift their sensitivity all the way down to, say, 3, those levels are going to change. And so now what's going to happen with a dramatically reduced microphone sensitivity is that the T level stimulation is going to occur at about 40 dB SPL. So the microphone of the processor is no longer picking up any sound below 40 dB. And the C level stimulation and compression is now occurring at about 80 dB. And so if someone has inadvertently reduced their sensitivity all the way down, they are now not hearing all of those soft sounds, and louder sounds are coming through without being compressed. And so we want to make sure that the sensitivity is being used appropriately. If you go to the opposite end of the spectrum, if you've now shifted your sensitivity up to 19, you've now got the sounds that are in the environment at about 10 dB SPL being presented at T level, and sounds around 50 are starting to be compressed. And so certainly if a child was to have inadvertently increased their sensitivity up to 19, that's going to have a fairly dramatic effect on speech and distorting quite a bit of conversational speech. There is also a volume control that is available, and what the volume control is doing is globally reducing those comfort levels by a percentage of the dynamic range. So it's trying to control that loudness. It's important to remember that a volume of 0 is not no sound. And I know that's way too many negatives for a sentence, but a volume of 0 is about 20% of the dynamic range reduction. So you're still using 80% of that dynamic range. And that is sometimes the situation for children very early on in the process where they experience some resistance to putting the processor on. We turn the volume down to 0, and the idea is, oh, well, there's no sound there, so they should be okay, and yet they still have a little bit of a negative response. So just keep that in mind, and certainly that kind of behavior should not occur. And for most children, they use a volume depending on the processor. The Freedom Sound processor, the volume of 9 is what's typical. And the current sound processor, the CP810 or the Nucleus 5 processor, we use a volume of 10. And that's to give them that full range of access to their electrical dynamic range. And you'll see if the volume control and sensitivity controls are fixed or not, and what the settings are that the audiologist used as the defaults. Those are also listed on the MAP summary report. So before I get into the how will I know when it's time for a MAP section, I just want to address some of the questions that have come through. So one of the questions is, why do most CI testing reports only show CI thresholds through 4,000 hertz? It would be helpful to know what the patient hears at higher frequencies. The reason for that is actually a limitation of sound field threshold testing. And so there may be some in situations when they're doing testing through the sound field, will they be able to test out to 6,000 hertz? But most of the speakers that are used for sound field threshold testing are not calibrated for 8,000 hertz. And so it's actually not a CI limitation, it's the testing environment limitation. How do you reduce the sensitivity with a cochlear implant? That is a button on either the sound processor itself or with the Nucleus 5 system, that processor that is adjustable through the remote assistant. And there is information on the Cochlear website. If you go into there are troubleshooting sections where you'll be able to have a virtual processor and remote assistant available to you to practice and see which buttons have what capabilities. And another question is, does the volume present as V and a number? On the Freedom processor, there will be a V at the bottom of the LCD screen with the number when you're adjusting the volume. On the CP810 processor, you're able to see the volume on the remote assistant. There is no display on the processor itself. And the next question is, what is the lowest dB threshold that should be obtained ideally? And that is the perfect segue into the next session. So I'm going to hold off on that one for just maybe 3 or 4 slides. So in looking at how you know when it's time for a map, we like to talk about baseline measures. So doing some kind of a daily listening check, making sure that the child is using the correct settings, so the correct volume and sensitivity. And also you can use more traditional audiometric tests as well, whether it's using some closed set speech perception tests, open set speech perception tests, or sound field audiograms. And I always encourage the audiologists that are doing the programming to obtain feedback back from school personnel. When I was in an implant center for 10 years prior to joining Cochlear, we knew that we were seeing that child for a snapshot of 45 to 90 minutes of their day, and we're not getting a clear picture of how that child was functioning with their device on a daily basis. And the only way that we could get that information was to receive that in from the professionals that were working with that child on a regular basis. And so I encourage that communication to go in both directions. So if you're in a situation where you have a child that you're working with and might have some concerns and haven't been in contact with the programming audiologist, feel free to contact them and make sure that they're aware of what it is that you're observing on a regular basis. From a sound field audiogram standpoint, what we typically see with a cochlear implant are thresholds between 15 and 25 dB HL, and they should be relatively flat. There has been studies that have been done that have found that those thresholds really need to be at least 35 dB or better to ensure good detection of all speech sounds. And again, what we're seeing with the current systems are definitely better than that. We don't want to see 0 dB thresholds, because then we're running into some situations where we may be affecting those minimum and maximum delivery of signal situations and compressing conversational speech unintended and causing some distortions of that presentation. The way that the threshold and comfort levels have been set do have a direct impact on where those sound field thresholds are going to be. And so that's why we tend to make sure that those are set appropriately when we're working with especially a young child, because we want to make sure that if the system is set correctly, that the input level that is here on shown with this blue dot, if that is being presented at threshold level, that needs to be audible. So in this situation, when the threshold and comfort levels are set appropriately, that 25 dB SPL of minimum sound that's being picked up is being presented at the softest level that this individual can hear. If their thresholds are set too high, what's going to happen is that input signal is being presented at a level that's inaudible to that recipient. And so by the time you increase your input level to maybe 35 or 40 dB SPL, that's what it's going to take in order for that recipient to be able to perceive that there's a sound there. And they're going to be, again, missing all of these really important soft sounds of speech. We always want to make sure that we are not picking up as much noise and or looking at the differences in the different processors in terms of how much information is being process. So we have more information that a wider range that's available with the current processors, the CP810 and the Freedom processors, than we did with the Sprint and the 3G processor. If you observe changes in performance, a decrease in their responsiveness, their speech is becoming slurry, they have lost the ability to repeat or discriminate the ling sounds, and changes in vocal quality, those are definitely signs that there may be something going on. There's also increases to, that you're looking at. Are they increase requests to repeat things being increased? Are they not wearing their equipment? Negative behaviors, typical kinds of changes in performance that you would be observing. The first thing I'm going to say is, while all of those things are really important, it's not always the map. There are a lot of other components that can contribute to this. Some of them are part of the implant and some of them aren't. So they're making sure that you're aware of any kind of changes at home or in the classroom, whether they're having a rapid development of other skills, maybe on the more of the motor side. Take a look and see if it's both their perception and their production that's being affected. And also, these are still kids that we're talking about, and so selective listening and just having a bad day are always things that we want to keep in mind when we're looking at what's taking place. And so there are a number of ways to check the equipment itself. We have monitor earphones, which enable you to listen to the microphone of the processor. And then the Freedom and the CP810 processors also have helper codes, as well as very descriptive icons on the remote to let you know what the problem could potentially be with the processors. You'll see through the next section of the slides that there are a number of troubleshooting steps and reminders, but again, I can't tout the troubleshooting on the website enough, and it does a much better job describing things because of the virtual capabilities of the web that are available that I can't do justice talking about. So I'm actually going to skip through these slides to get to the last section so that we can still have a few minutes for any additional questions. Once you've gone through that troubleshooting and determined, okay, all of the external equipment is fine, we've eliminated all of the other variables, I really do think this is a mapping change that needs to take place. What the center will then do is they will rerun the impedances to see if there's been any changes in that, because if there's been a change in the impedance, that could potentially change your compliance and change whether that map is still as effective as it should be. They'll also take a look at the threshold and comfort levels to see if those have changed, and then do a evaluation to compare their speech perception testing previously to where they are today. In more complex cases, that clinic may also request assistance from a clinical representative of Cochlear, and then we'll come in and do some additional testing if necessary. Here is the link for that wonderful interactive troubleshooting guide. Some additional places that you have resources available to you as well is through the 800 number for Cochlear. There is an on-call audiologist available from 6 a.m. to 6 p.m. Mountain Time every day. And there are part numbers listed here for troubleshooting guides, which are brochures or manuals that you can go through as step-by-step troubleshooting, as well as troubleshooting kits, which are one-stop kits of all of the extra parts and pieces that one would need to troubleshoot the different processors that are available as well, and all of those are available through Cochlear. Um, we've got another question that has just come up. How do audiologists determine a soft failure to a device? So there are some tools that are available for us from each of the cochlear implant manufacturers, and additional test pieces of equipment that we bring in and run diagnostic tests on the internal devices to see if we are able to pick up any kind of problems with those devices. And one of the other key aspects that are looked at, especially with problems that may not be as clear-cut, is to look at how the individual is performing with their device. And so doing some of those comparisons of baseline speech perception measures and where they are performing currently to help with the evaluation of whether that device is operating appropriately or not. Another question is, can anyone access the online virtual processor and troubleshooting guides, or is it only available for clients who have a specific processor? That is available to anyone. So you would choose which processor it is that you want the troubleshooting guide for. But once you've specified that, the virtual processors, you can choose whether you want to do unilateral versus bilateral. And then also, because the remote has both a basic and an advanced setting, you can choose which one of those you want to have available to you as well. And then I had another question about addressing the smart sound option and FM. So what the recommendation is for individuals who are using a dynamic FM is that they have a map that has both ADRO and auto sensitivity enabled in their maps. And so that will enable the dynamic component of the FM system to work to its maximum functionality, along with the processor working to its maximum functionality as well. And that's based on some research that has been done looking at the performance of individuals using dynamic FM, both with and without those options enabled. The next question is, what is IIDR? And on the handout, do all dB levels refer to SPL? So IIDR is instantaneous input dynamic range. And so that is the amount of acoustic information that's being processed at any one instant in time through the system. And I'm going to say for the most part, yes, all of the dB levels do refer to SPL unless they are indicated otherwise. And then another question is, when you increase pulse width, is there a change of perception or clarity, negative or positive? And typically no. And that has to do with the fact that we're able to maintain that loudness. There are some times where we've gone to a very dramatically different pulse width where an individual will notice a change, but typically there is, after a brief acclimatization period, able to adjust to that new pulse width and continue to progress with their device. So the slide that's up now is showing our next two upcoming Hope online events. So Tuesday the 25th is auditory identification with Ashley Garber. And then on Friday, November 4th, we will have a session on parent and adult habilitation resources that are available in Spanish.